Hello students, in this video we have assignment 6.2. There are 6 questions in this assignment, but we will divide it into 3 videos. In this particular video, we will take up question 6, which is talking about motional EMF and its expression. In next video, we'll discuss origin of induced EMF and law of conservation of energy in the phenomena of electromagnetic induction. And in third video, we'll talk about eddy current. So just one small topic, motional EMF in this video. Let us start. In previous video session, we saw that whenever you have any flux linked with coil, suppose I have a coil and if I keep magnet close to it, we know that magnetic field lines do pass through the loop or given coil, right? And what is the condition for EMF to be induced in this coil? Condition is you will have to change the flux link, the number of field lines linked with the coil. If you can somehow change, you can say you have changed flux. What is the expression for flux? Phi is equal to BA cos theta. So to change flux, you can either change B. How to change B? Two ways of changing magnetic induction. Either change position of magnet or move magnet, or else move coil. Okay, so there should be relative motion between magnet and coil. Then B can be changed. Second option is change area of the coil. That is what we are going to do in today's topic. And third way is to change theta. How to change theta? What you can do is rotate coil. That is what is done in AC generator. So wherever you have motion involved to produce electromagnetic induction, it is the induced EMF is called motional EMF. In today's topic, we will be changing area, and that is how we will change flux. Once flux is changed according to Faraday's law, we can find out induced EMF by this formula delta phi by delta t, or else for small change in flux, sorry, this is average, and for instantaneous we take d phi by dt. What this negative sign indicates? It is consequence of Lenz's law. Okay, so consider that we have a U-shaped wire almost, and it is placed between two magnet. So let the north pole of the magnet be placed here, and let the south pole be below. Now, as we can see here, magnetic field is in downward direction, and I assume that this part of this loop is of L length, and now I place a conducting rod here. Where I have placed conducting rod, let me consider that the rod is placed in such a way that this distance is x. Okay, now can I say there is flux linked with this enclosed part? Where is the enclosed part? Here is the enclosed part. This is the enclosed part. Okay, so how much is the flux linked? So we can say that flux linked is BA cos theta. So B is B only. How much is area? Area is L into X. And considering area vector to be in downward direction, angle between B and A is 0. So cos theta is cos 0, that is 1. And hence it is BLX. This is the flux link. Now, what if I move? What if I move this rod with, say, velocity v? Now, as I move the rod, suppose if I take it at some point here, how far you have taken it? So let me consider that I have shifted the rod by distance delta x. So obviously I'm changing area, and if area is changed, there is change in flux, and then we can expect induced EMF. So how much is the induced EMF? average induced EMF is minus delta phi by delta t. Okay, so minus B L delta x upon delta t. See, in this case, when you move the rod, which quantity you are changing? You are not changing B. Magnets are same. You are not changing L. This part is same. Okay. So, which quantity is changed? We are changing X, and hence change in flux is because of change in X. So, this is the formula, and if I take delta t tends to 0, if I take time duration very small, then this equation can be written as epsilon is equal to minus B L dx by dt. Okay, this can be written as minus B L delta x by delta t. And for small change in time, delta x by delta t can be written as dx by dt. What is dx by dt? Dx by dt is nothing but velocity of the rod, so it is minus BVL. This is the expression for motional EMF, which says that induced EMF depends on strength of magnetic field, that is B. It depends on how fast you are changing flux, which is characterized by V. Okay, if you move this rod very fast, you are changing flux at faster rate, so induced EMF will be more, and it depends on L. Okay, L is length of this rod. So that is all about induced EMF, and there is one more way of expressing this induction process, which we will discuss in next video in the origin of induced EMF. For now, this is the topic. I hope you could understood. Now, in next session, we'll see one more reason behind induction process. Okay, thank you.